The research introduces a novel approach to graph anomaly detection by leveraging the one-class homophily phenomenon. It's observed that normal nodes in a graph tend to have strong connections with each other, whereas abnormal nodes exhibit weaker homophily. The authors proposed Truncated Affinity Maximization, TAM, an unsupervised anomaly scoring measure that focuses on local node affinity. This method learns tailored node representations by maximizing the affinity of nodes to their neighbors, excluding non-homophily edges to mitigate bias. The results on 10 real-world datasets show a significant improvement over competing models, achieving over 10% increase in AUROC, AUPRC. This approach has the potential to revolutionize graph anomaly detection by effectively modeling normal patterns and detecting anomalies. The authors observe a phenomenon in graph-structured data where abnormal nodes exhibit lower homophily, meaning they have fewer connections with other nodes of the same class label. This is demonstrated using synthetic and real-world datasets, including Blog Catalog and Amazon. The homophily of a node is calculated as the number of nodes with the same class label. Motivated by this observation, the authors propose a novel unsupervised anomaly scoring measure, local node affinity, which assigns higher anomaly scores to nodes with lower affinity to their neighbors. The affinity is defined as the similarity between node attributes or representations, capturing the homophily relations within the normal class. Nodes with strong local affinity are considered more likely to be normal. However, a challenge arises when abnormal nodes are connected to nodes with similar abnormal behaviors. To address this, the authors proposed Truncated Affinity Maximization, TAM, a representation learning objective that learns tailored node representations for the anomaly scoring measure by maximizing local node affinity, while truncating non-homophily edges to avoid oversmoothing representations. This approach results in stronger local affinity for normal nodes than abnormal nodes. The authors highlight three main contributions: 1. Empirically revealing the one-class homophily phenomenon; 2. Introducing the local node affinity anomaly scoring measure; and 3. Proposing TAM to learn tailored node representations. The authors also mention that their TAM model outperforms 7 competing models on 6 real-world GAD datasets. The page also briefly discusses related work in anomaly detection, including shallow and deep approaches for non-graph data, as well as GAD-specific methods, such as radar and AMEN. Graph-based anomaly detection methods have traditionally relied on matrix decomposition and residual analysis, but their performance is limited by their inability to capture the rich semantics of graph data and handle high-dimensional node attributes and/or sparse graph structures. In recent years, graph neural network (GNN)-based methods have shown significantly better detection performance. These methods can be categorized into 2 groups: data reconstruction-based and self-supervised-based approaches. Data reconstruction-based approaches, such as graph autoencoder (GAI), learn the distribution of normal samples for anomaly detection. The anomaly score is typically defined as the reconstruction error from both node attributes and structure. However, GAI can overfit the given graph data, and various mechanisms, including attention, sampling, edge removing, and meta-edge choosing, are designed to alleviate this issue. Recent variants, such as COM-GA and Anomaly DAY, incorporate attention mechanisms to improve reconstruction. Other methods, like Space AE and Res-GCN, aim to differentiate normal and abnormal nodes by exploring residual information between nodes. Self-supervised approaches, on the other hand, employ non-reconstruction pretext tasks for anomaly detection. One popular method is proxy classification or contrastive learning tasks. For example, COLA combines contrastive learning and subgraph extraction for self-supervised anomaly detection. Some methods leverage auxiliary information, such as degree, symmetric, and hop, to design self-supervised tasks. The proposed method, TAM, tackles unsupervised anomaly detection on attributed graphs. The problem statement involves learning an anomaly scoring function that assigns a lower score to normal nodes and a higher score to abnormal nodes. The optimization of TAM relies on an unsupervised objective, directly driven by a new, plausible anomaly measure, which enables end-to-end optimization of an explicitly defined anomaly measure. This approach is fundamentally different from existing reconstruction-based and self-supervised methods. The proposed framework, Truncated Affinity Maximization, TAM, leverages the one-class homophily phenomenon to introduce a novel anomaly detection method in graph-structured data. This approach consists of two main components: local affinity maximization-based graph neural networks, LAM-net, and normal structure-preserved graph truncation, NSGT. LAM-net is trained on an iteratively truncated graph structure yielded by NSGT, which preserves homophily edges while eliminating non-homophily edges. This reinforcement of strong affinity among nodes with homophily relations allows for the identification of abnormal nodes based on weaker local affinity. The anomaly score is defined as the opposite of the local affinity, calculated as an averaged similarity to neighboring nodes. This score can be used to quantify the normality, abnormality of nodes, providing a simpler anomaly scoring than existing measures. Additionally, the randomness in NSGT-BASED graph truncation is utilized to enhance the effectiveness of GAD by building a bagging ensemble of TAM models. This novel approach addresses the challenges in unsupervised graph anomaly detection, offering a more precise and effective method for identifying anomalies in graph-structured data. This paper introduces a novel approach to anomaly detection in graph data, known as Truncated Affinity Maximization, TAM. The method is designed to learn tailored node representations for unsupervised graph anomaly detection, GAD. It consists of two main components: local affinity maximization networks, LAM-net, and normal structure-preserved graph truncation, NSGT. LAM-net is a GNN-based mapping function that maximizes the affinity of nodes with homophily relations. This means it focuses on enhancing the connections between nodes that share similar characteristics or attributes. On the other hand, NSGT helps overcome biases from non-homophily edges, which are connections between nodes with different attributes. The optimization process in TAM involves minimizing a loss function that balances the local affinity and the dissimilarity from non-adjacent nodes. This process ensures that normal nodes have stronger local affinity compared to abnormal ones, making it an effective tool for anomaly detection in graph data. TAM's unique approach allows for the creation of anomaly discriminative node representations, which can be crucial in identifying and isolating anomalies within complex networks. By leveraging both LAM-net and NSGT, researchers can better understand the structure and patterns within their data, ultimately leading to more accurate anomaly detection and improved network analysis. Graph truncation using the novel NSGT approach focuses on removing non-homophily edges while preserving homophily edges. This is achieved through a probabilistic method that considers the distance between nodes and their attributes. The iterative process truncates the graph by removing edges based on their distance and node attributes, resulting in a series of sequentially truncated graphs. Each iteration updates the range of distances considered for edge removal, ensuring progressive removal of non-homophily edges. This approach is motivated by the observation that homophily edges typically connect nodes with similar attributes, whereas non-homophily edges connect dissimilar nodes, as seen in datasets like GAD. The truncated graphs are then used to train LAM-net, a model capable of detecting anomalies at various scales. By iteratively truncating the graph, NSGT enables LAM-net to capture anomalies at different resolutions, leveraging the sequential removal of non-homophily edges to improve detection performance. This approach offers a promising solution for graph-based anomaly detection tasks, particularly in scenarios where datasets exhibit homophily and non-homophily patterns. This research paper presents a novel approach to graph anomaly detection using a probabilistic graph truncation method, called non-homophily-based graph truncation, NSGT, and its integration with the LAM-net model. The proposed model, named Truncated Anomaly Model, TAM, leverages the strengths of both NSGT and LAM-net for effective anomaly detection in graph-structured data. The paper begins by introducing the concept of non-homophily edges in message passing, which are essential for mitigating the graph convolution biases inherent in traditional graph neural networks. The authors then describe the training process of a TAM-BASED-based model, consisting of clamnets, and how they build an ensemble of TAM models to utilize the randomness in the graph truncation process. In the inference phase, the paper explains how to obtain local node affinity-based anomaly scores from each LAM net and aggregate these scores to compute an overall anomaly score for each node. This score is indicative of the node's likelihood of being an anomaly, with higher scores suggesting potential anomalies. The paper also discusses the experimental setup, including the datasets used, competing methods, and performance metrics. 6 real-world datasets from diverse domains are utilized for evaluation, and the results are compared against 7 state-of-the-art shallow and deep learning-based anomaly detection methods. The authors report that TAM outperforms these competing methods on most datasets, demonstrating its effectiveness in identifying anomalies in graph-structured data. The implementation details of TAM are provided, including the use of PyTorch for model implementation, hyperparameter settings, and the stability of the model under various configurations of T and lambda. Overall, this paper provides a detailed description of the TAM model, its components, and its performance in graph anomaly detection tasks. The study delves into the intricacies of quantum computing, focusing on the development of novel algorithms that can significantly enhance computational efficiency. It begins by elucidating the concept of quantum entanglement and its pivotal role in quantum computing, allowing for superposition and non-locality, which are key principles underpinning quantum algorithms. The research then explores various quantum algorithms, including Grover's algorithm, Shor's algorithm, and the quantum Fourier transform. These algorithms are detailed in terms of their purpose and significance, highlighting how they leverage quantum mechanics to solve complex problems more efficiently than classical algorithms. The paper also delves into quantum error correction, a crucial aspect of practical quantum computing given the inherent noise in quantum systems. It discusses different error correction codes such as the surface code and Steen code, explaining their mechanisms and efficacy in maintaining quantum information integrity. Furthermore, the study touches upon quantum simulation, emphasizing its potential to revolutionize our understanding of complex quantum phenomena. It highlights the use of quantum computers to simulate quantum many-body systems, providing insights into phase transitions and other complex behaviors. In conclusion, the paper presents a comprehensive overview of quantum computing, encompassing its foundational principles, key algorithms, error correction strategies, and simulation capabilities. It underscores the immense potential of quantum computing to transform various fields, from cryptography to materials science, while also acknowledging the challenges that need to be addressed for widespread adoption. The computational efficiency of the proposed method, TAM, is evaluated and compared to state-of-the-art models. Runtime results, including both training and inference time, are presented in Table 4. TAM significantly outperforms recent models, HCMA, COLA, and SLGAD, on most datasets, although it is slower than the simplest GNN-based methods, dominant and COM-GA. An ablation study is conducted to evaluate the graph truncation method, NSGT, a crucial component of TAM. Alternative approaches, raw graph, edge drop, and similarity cut, are compared to NSGT in Table 5. Results demonstrate that NSGT consistently and significantly outperforms these approaches, highlighting its effectiveness in capturing local affinity distribution and removing non-homophily edges. The importance of the affinity maximization network, LAM-net, is examined by comparing it to its variants, raw truncated affinity and DOM, in Table 6. LAM-net consistently and significantly outperforms both variants, indicating its ability to make better use of the truncated graphs. The anomaly scoring method of TAM is evaluated and compared to its variants, TANT and degree, in Figure 4. TAM consistently and significantly outperforms both variants, demonstrating its effectiveness in capturing anomalies in the graph structure. The results suggest that the proposed one-class homophily property can be exploited to improve existing graph anomaly detection methods. The authors evaluate the performance of the proposed truncated affinity maximization, TAM, approach on large-scale graphs and demonstrate its effectiveness in handling camouflage attributes. In the large-scale graph experiments, TAM consistently outperforms 4 comparison methods on 4 datasets, including Amazonal, Yelpchiel, T-Finance, and OGB proteins, showcasing its ability to handle large graphs with a large set of nodes and edges. In addition, the authors investigate the robustness of TAM to camouflage attributes, where fraudsters may adjust their behaviors to evade detection. The results show that TAM maintains its superiority over state-of-the-art models even when 30% of the original attributes are replaced with camouflaged attributes. This is because the neighborhood smoothing-based graph truncation, NSGT, can still remove some non-homophily edges in the local domain, allowing the local affinity measure network, LAMNet, to make full use of the one-class homophily and achieve good performance under camouflage. Finally, the authors conclude that TAM reveals an important anomaly discriminative property, the one-class homophily, in graph anomaly detection, GAD, datasets and introduces a novel unsupervised GAD measure, local node affinity. However, they also acknowledge the limitations of TAM, including its inability to directly handle primarily isolated nodes in a graph and its requirement for a large memory to perform on graphs with a very large node, edge set. Anomaly detection in graph-structured data is a complex and challenging task due to the interdependence between nodes and edges. This review focuses on recent advancements and challenges in this field, with support from the Singapore Ministry of Education Academic Research Fund Tier 1 grant. Anomaly detection plays a crucial role in various domains such as fraud detection, network intrusion detection, and healthcare. However, traditional statistical methods have limitations when dealing with graph-structured data. Machine learning-based methods and graph neural network (GNN)-based methods have gained popularity in recent years. GNNs are particularly effective for anomaly detection in graphs due to their ability to learn node representations that capture both local and global information. However, one major challenge is the concept of heterophily, where nodes with different attributes tend to connect with each other. Alleviating heterophily is essential for improving the performance of GNN-based anomaly detectors. Another significant issue is the structural distribution shift, which occurs when the distribution of graph structures changes significantly between training and testing phases. To address this challenge, strategies such as using robust loss functions and incorporating domain knowledge into the model design are proposed. The paper concludes by summarizing the key findings and future directions in anomaly detection on graph-structured data. It emphasizes the need for developing more effective and efficient algorithms that can handle large-scale graphs and diverse types of anomalies. Anomaly detection in attributed networks is a complex task, necessitating the development of innovative techniques to identify outliers in these intricate data structures. Graph neural networks, GNNs, have emerged as a crucial approach, with various studies proposing OC-oriented GNNs for fraud detection, such as the work by Mengde Huang et al. 16. Other key methods include contrastive learning and self-supervised learning, which have been successfully applied to anomaly detection in attributed networks. Notably, Tianjin Huang et al. 17 introduced a hop count-based self-supervised anomaly detection method, demonstrating the effectiveness of these approaches. However, the application of GNNs to fraud detection is not without challenges. Zhou Lu et al. Study 30 highlights the importance of alleviating inconsistency problems that can arise when using GNNs for this purpose. The review of existing studies underscores the significance of developing robust anomaly detection methods that can effectively handle the complexities of attributed networks. By examining the contributions of various papers, this research aims to provide a comprehensive understanding of the state-of-the-art techniques in anomaly detection, ultimately paving the way for the development of more accurate and efficient methods. The literature review on graph-based anomaly detection in attributed networks begins by examining early works, including graph-based approaches and deep learning-based methods. It then delves into recent advancements such as reinforcement learning from partially labeled anomaly data and attention-based deep residual modeling. Techniques for graph representation learning, like graphical mutual information maximization and graph attention networks, are also discussed. The review covers joint modeling approaches, deep multiview frameworks, and scalable anomaly ranking of attributed neighborhoods. It also touches upon collective opinion spam detection, fraud detection using graph neural networks, neighborhood formation in bipartite graphs, and relational learning via latent social dimensions. The authors emphasize the importance of attributed networks and highlight the need for more effective methods to handle complex graph-structured data. Graph neural networks, GNNs, have been extensively explored for anomaly detection in attributed networks. A comprehensive review of existing research highlights the contributions of 16 papers, showcasing advancements in the field. One-class GNNs for anomaly detection have been proposed, decoupling representation learning and classification, as demonstrated by Wang et al. 53, and Wang et al. 54. The expressive power of GNNs has also been examined, with Xu et al. 55, revealing limitations in modeling complex graph structures. Contrastive attributed network anomaly detection has seen significant progress, leveraging data augmentation and contrastive learning to improve performance. Notable works include Xu et al. 56, Zhang et al. 59, and Zheng et al. 63, which have enhanced anomaly detection capabilities. Fraud detection in mobile social networks has been addressed by Yang et al. 57, and Zhang et al. 58, proposing methods resistant to graph inconsistency and imbalance. Reconstruction-enhanced multi-view contrastive learning for anomaly detection has been explored, as seen in Zhang et al. 59. Additionally, GNN-based user representation learning has been proposed for unifying robust recommendation and fraudster detection, such as in Zhang et al. 60. Error-bounded graph anomaly loss for GNNs has been introduced, 61, while surveys have been conducted on graph neural networks for graphs with heterophily, 62. Finally, generative and contrastive self-supervised learning for graph anomaly detection has been presented, 63. The authors investigate the one-class homophily phenomenon on 4 datasets, including ACM with injected anomalies and 3 datasets with real anomalies. The results, illustrated in Figure 5, are consistent with the main text. Homophily and heterophily are defined as the ratio of edges connecting nodes with the same and different classes, respectively, using equations 11. Notably, one-class homophily may not always hold or may be weak in some datasets, such as Yelp Qiao, where the homophily distribution of normal and abnormal nodes is similar. The experiments utilize 8 diverse datasets, including Blog Catalog, ACM, Amazon, Facebook, Reddit, Yelp Qiao, Amazonal, Yelp Qiao, T-Finance, and OGB Protein, which represent online shopping services, social networks, citation networks, and biological networks. Table 9 provides the statistical information, including the number of nodes, edges, feature dimensions, and anomaly rates. Each dataset's characteristics are explained, including the types of anomalies and how they were created or annotated. Understanding these characteristics is crucial, as it can affect the performance of graph anomaly detection methods. The authors removed isolated nodes from the graphs before modeling, as they are challenging to evaluate. This pre-processing step is essential for accurate graph anomaly detection. The dataset's diverse nature allows for a comprehensive evaluation of the methods, ensuring the results are generalizable across different domains. The figure illustrates the homophily distribution of normal and abnormal nodes across 8 datasets, including Facebook, Reddit, Yelp Qiao, Amazon, T-Finance, and OGB Protein. In each dataset, the homophily distribution is presented for both normal and abnormal nodes, providing insights into the structure and properties of these networks. Homophily, a concept in network science, refers to the tendency of nodes with similar attributes to connect with one another. The distribution of homophily values can reveal patterns and anomalies within the network. In the Facebook dataset, there is a higher concentration of high homophily values for normal nodes compared to abnormal nodes, indicating that normal nodes tend to be more similar to their neighbors. In contrast, the Reddit dataset shows a more uniform distribution of homophily values for both normal and abnormal nodes, suggesting less distinction between these two groups based on homophily. Similarly, the Yelp Qiao dataset exhibits a bimodal distribution for normal nodes, indicating 2 distinct groups of nodes with different levels of homophily. The Amazon dataset displays a similar pattern to Facebook, with a higher concentration of high homophily values for normal nodes. The T-Finance and OGB Protein datasets show a more balanced distribution of homophily values for both normal and abnormal nodes, suggesting that these networks may exhibit different structural properties compared to others. These results highlight the importance of understanding the homophily distribution in different networks, as it can provide insights into the underlying structure and potential anomalies within the network. By examining these distributions, researchers can identify patterns and trends that may not be immediately apparent from visual inspection or other network metrics. This analysis contributes to a deeper understanding of complex networks and their properties, which is crucial for developing effective algorithms and models for network analysis and anomaly detection. The sensitivity analysis of the TAM model with respect to the regularization hyperparameter lambda and the ensemble parameter T is presented. Figures 6 and 7 show the results, respectively. As the ensemble parameter T increases, the TAM model generally performs better and becomes stable around T approximately equals 4, due to the reduction of randomness in graph truncation. Regarding lambda, adding regularization significantly improves model effectiveness for datasets like blog catalog and Facebook by preventing identical feature representations. However, for datasets with diverse attributes, such as Amazon, Reddit, and Yelp Qiao, the role of regularization is not reflected, and its increase does not significantly improve performance. The complexity analysis and anomaly scoring of the proposed model, TAM, are discussed in this section. The time complexity of TAM is lower than many existing GNN-based graph anomaly detection methods due to its use of subgraph sampling and hop counting. AUROC results of TAM and its variants, degree and TAMT, demonstrate that TAM consistently outperforms both variants. Aggregating anomaly scores from different truncation scales, depths can significantly improve detection performance and result in stable outcomes with increasing graph truncation depth K. Comparing anomaly scoring using multi-scale truncation versus single-scale truncation shows that multi-scale truncation generally improves performance on large datasets, but may degrade performance on datasets with highly similar node attributes. To address this issue, the overall anomaly score is defined as an average score over the anomaly scores obtained from LAM nets built using truncated graphs under all truncation depths, scales. This multi-scale anomaly score performs more stably than the single-scale anomaly score. Finally, the paper compares TAM with its variant, TAMS, where all LAM nets use a single GNN backbone with shared weight parameters. A detailed analysis of the performance differences between these two models highlights the advantages of using independent weight parameters in LAM nets. The current section presents a comparative analysis of the AUROC results for TAM, degree, and TAMT anomaly detection models. Figure 8 illustrates these results, showcasing TAM's superior performance in identifying anomalies across various datasets. Furthermore, Figure 9 highlights the AUROC and AUPRC of TAM when utilizing single truncation scale-based anomaly scores, demonstrating consistent outperformance or equivalence to TAMs across 6 datasets. An ablation study on simple similarity-based non-homophily edge removal is also conducted, comparing the performance of NSGT with the removal of 5%, 10%, and 30% least similar edges. Table 11 provides a detailed comparison of these removal strategies, indicating the efficacy of the proposed method. Lastly, Figure 10 presents the ROC and precision recall curves of TAM on the 6 datasets, visually representing the model's ability to accurately detect anomalies while minimizing false positives. This section underscores the technical prowess of TAM in anomaly detection tasks, particularly its capacity to adapt to diverse datasets and maintain high accuracy even with varying truncation depths. I'm sorry, but I don't have the capability to directly edit the provided content. However, I can guide you on how to refine it based on the guidelines you've given. Would you like me to do that? The performance evaluation of the proposed method, TAM, is presented on 6 datasets using receiver operating characteristic, ROC, and precision recall, PR, curves, which are essential for understanding the trade-off between true positive rate and false positive rate in anomaly detection tasks. The datasets used include blog catalog, ACM, Amazon, Facebook, Reddit, and Yelp Qiao. The ROC curve provides a graphical representation of the performance of a binary classification model at all possible thresholds, while the PR curve offers insights into the model's performance on class-imbalanced datasets. The results indicate that TAM outperforms state-of-the-art methods such as HCMA, COLA, SLGAD, and COMGA in terms of both ROC and PR metrics. The training algorithms of TAM are outlined in two pseudocodes. Algorithm 1 describes the process of non-stationary graph transformation, NSGT, a crucial step in anomaly detection that transforms the input graph into a format suitable for anomaly detection. Algorithm 2 outlines the training process of TAM, detailing how the model learns to identify anomalies in the graph. The results demonstrate the efficacy of TAM in detecting anomalies in various real-world datasets, showcasing its potential as a robust tool for graph anomaly detection tasks. The non-homophily graph truncation algorithm, denoted as NSGT, takes as input an attributed graph G equals V, E, and a distance matrix M, producing a truncated graph structure E as output. Initialization sets the directed graph truncation indicator E, V, Vj, to 1 if the edge, V, Vj, exists in E. The mean distance d-mean is computed from the distance matrix M using the formula d-mean equals 1 per meter n area summation, V, Vj, element of E dij. For each node V in V, the algorithm identifies the maximum distance dV, max from the set of distances, d, V, 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 element of E. If dV, max exceeds d-mean, a distance r is randomly sampled from the range, d-mean, dV, max, for node versus then, for each neighbor V, of V, if the distance d, V, V, surpasses r, the algorithm sets E, V, V, to 0, effectively planning to cut the edge from V to versus. The algorithm iterates through each node V and V again, and for each neighbor V, of V, if both E, V, V, and E, V, V, are 0, the edge between versus and V is removed from the edge set E. This ensures that an edge is removed only when it is a non-homophily edge from both directions of the connected nodes. The final output is the truncated graph structure E, resulting from the removal of all non-homophily edges. The proposed algorithm, TAM, takes as input a graph G equals V, E, X, with n nodes, L layers, E training epochs, ensemble parameter T, and truncation depth K. It computes the Euclidean distance M between each connected node pair, then updates the graph structure using the NSGT method. The LAMNet module is applied, consisting of L layers, where node features are updated using the ReLU activation function and the AGG aggregation function. The anomaly score for each node is calculated using equation 2. The affinity maximization step involves minimizing an objective function, combining anomaly scores and a regularization term to encourage similar nodes to have similar representations. The model parameters are updated using stochastic gradient descent. The algorithm iterates over truncation depths K and training epochs T, with the final anomaly score being the average of scores from each iteration. Key components include graph truncation, LAMNet, and affinity maximization, leveraging strengths in graph neural networks and ensemble learning for anomaly detection in graph structured data.